Really an honor for me, as always, to stand up here and say a few words. Right now, I just want to say a few words about our distinguished speaker, Professor Chris Barty, who joined UC Irvine faculty less than a year ago?
July last year.
July of last year. He is what we call the first professor in the Convergence of Optical Sciences Initiative, known as COSI. And it's kind of been led by the Beckman Laser Institute and the Medical Clinic, which has been run by Bruce Trumberg, who many of you have known. We've been there many times, and who is now leaving UC Irvine to go to the National Institute of Health as a director there. But Chris came to us from Lawrence Livermore Laboratories, and there he was the chief technical officer for the NIF facility in the Photon Sciences Directorate. So he came down to UC Irvine to be away from the area up there and to lead UC Irvine in converging optical sciences, right? So as you all know, that's what we do, and it's been kind of one of my, I suppose, dreams of having UC Irvine optics community converge. And when I met Chris at the Beckman Laser Institute, after reading about him in a particular newsletter of theirs, I said, I got to meet this guy. I got to bring him over here. And so here we are. There's quite a bit of more detailed information about Chris and his background on a particular, on the SPIE profile. He's a fellow of SPIE. He also is an OSA member, fellow of OSA. And most recently, he won the Harold E. Eddington Award at OSA for the advancements of ultrafast lasers. And he is the founder of a company here in Irvine now, and also in Australia. And it's called
Lumitron.
Lumitron. And they're involved with X-ray lasers, X-ray sources. And he'll be telling us about that tonight. And there are some people here that work with him. And I'm going to let him go ahead and take it from there so he can tell you more about all these wonderful. Thank you very much for being here tonight.
Thanks. It's my pleasure to be here. I wanted to, because I'm an optics geek, I wanted to back up one slide. Although it doesn't look like it's going to allow me to back up slides here. They seem to be frozen. We have lost the ability to do anything. Let's see if I take that out, if it's going to change. Now that backed up. Okay, I wanted to back up and show this one picture. I was 2 weeks ago, Monday, I was in DC at the Frontiers in Optics meeting. I had just won the R.W. Wood Award of OSA, and the person that nominated me is the person in this selfie. I think this is probably the last selfie that Gerard Moreau had taken of him before he won the prize, the Nobel Prize, this following Tuesday. The other thing I wanted to say about this was the person who shared the prize for CPA with him was a woman named Donna Strickland, who I've known for a long time. Donna won the prize for the work she did as a grad student. So all you grad students out there, that's all we expect of you is to, win the Nobel Prize, okay? I'm going to talk about the Convergence Optical Sciences Initiative and compact Laser-Compton light sources, mainly about the compact laser light sources. I'm a professor in physics and astronomy here. I have an appointment via the Beckman Laser Institute in the Department of Surgery. I'm a member of the Chow Family Comprehensive Cancer Center here on site, and I'm the lead hire in this Convergence Optical Sciences Initiative. For those of you who don't know, the background picture here is actually the most famous Jackson Pollock, which is called Convergence, which I thought was very appropriate for this meeting. You are here at UCI. That's where the continuing education building is. I want to talk a little bit about COSI. COSI was the provost, Lavernia, Enrique Lavernia, put out a call a couple of years ago for targeted hiring initiative. And what he was asking for was any department on campus or any group of people on campus to suggest a cluster hire in a particular area. Bruce Tromberg, Shal Mukamel, who's a National Academy chemist in the chemistry department here, and Toshi Tajima, who's a physicist in the physics department, put together the Converge Optical Sciences Initiative. And that initiative suggests that you look at the intersection of physical science, engineering, medicine, biology, and industry all around some advanced optical science. In my case, that advanced optical science is Laser-Compton X-ray Sources. Lavernia selected that as the winning initiative, and I was targeted as the senior hire of that 5-hire package. There are 4 junior faculty positions, 3 of which have yet to be filled, 1 of which we're in negotiations with a person, but there will be a call for a physical sciences junior faculty hire this year, so optical sciences in the physical science realm, and there'll be one in photonics for cancer research as well. That's part of that activity. COSI will move with applied innovation. For those of you who've been to applied innovation in the past, I hear you've held your meetings at the Cove before. Applied innovation is moving out of its 44,000 square foot building in the research park into a 100,000 square foot building that Broadcom vacated in May of this year. And that renovation of that building will be complete, I think, in April now is the projected date. The COSI faculty will have 10,000 square feet of lab space in that building, and so we'll all be located over in that space. And of course, that's very convenient to campus and very convenient to the Med Center, very convenient, of course, to applied innovation because we'll be right there. I will say, and this is where I think there's a strong connection to this audience, the COSI initiative really wanted to emphasize the connection into industry. For those of you who've been to applied innovation, it really is a pretty impressive entrepreneurship engine. They're really well set up to try and facilitate people taking new ideas and getting them out into new business. I taught for 4 or 5 years at Stanford, and Stanford is well known for entrepreneurship. I think what I've seen here takes it another level. It's really quite impressive what's going on. I'm quite enthused about the possibilities here in Orange County. I came from Lawrence Livermore National Lab. Lawrence Livermore National Lab is about 45 miles east of San Francisco. It has a 1 square mile campus in Livermore. Sometimes that campus is called the smartest square mile on earth because it's got 5,000 PhDs or so in that square mile. We like to tell that to Los Alamos a lot, right? But of course, they're spread out over a lot more areas, so that doesn't really count. Lawrence Livermore is one of the 3 nuclear weapons science labs within the Department of Energy's National Nuclear Security Administration. NNSA is a $15 billion per annum organization. Sandia, Livermore, and Los Alamos are all nominally $2 billion a year activities. So think of it as a big company. Now, everybody normally thinks that LL&L stands for the thing that we put on the label, but anybody who's ever been to Livermore knows that L&L stands for lasers, lasers, nothing but lasers, right? And that's because the whole north end of campus is Laserland. There's been a laser directorate at Livermore since 1972, and there have been roughly 1,000 people working in lasers and optics since 72, so there's more than 45,000 person years of experience in lasers and optics at that site. The National Ignition Facility is the premier laser facility on that site, which is the big building at the bottom, about the size of a large football stadium, sports arena. There are roughly 1,000 people associated with the NIF directorate. It was the largest successfully completed project ever in the Department of Energy. It's the highest energy laser in the world. Each laser beam of the 192 laser beams is the highest energy laser beam in the world, and you've got 192 of them in the system. It also was a very well managed project. It actually won the International Project of the Year award in 2010. It beat out the Dallas Cowboy football stadium and some state-of-the-art hospital in Europe. Inside of that facility is a 10-meter diameter chamber. We fire the 192 beams into the center of that chamber onto a target that looks like this. Fire to the inside walls of this can, and there's a pellet of a couple of millimeters in diameter. We create X-rays. The X-rays cause the pellet to ablate. The ablated pellet causes a rocket motion inwards. And at the point of stagnation, you create a density that's 1,000 times liquid density and a temperature that's only found in the center of the sun. And you get fusion to occur, right? And so the goal of that facility is to try and get more fusion energy out of the neutrons than the laser energy that went in. The outside of the facility is, as an optics geek, you got to appreciate this thing. There was 6,204 line replaceable units. One of these things that the guy standing in front of is a line replaceable unit. There's a factory that builds these things at Livermore. It was really an impressive feat to put all this together. Of course, this all looks very, very techy. And in fact, we had some people in management who had connection to Hollywood, and they came by and saw it and said, yeah, that does look techy. We're going to use it as the backdrop. So it was the backdrop for the Star Trek Into Darkness movie, if you've ever seen that movie. The NIF target chamber is the warp core of the Enterprise, right? So they came in a 2-week period. We had a downtime for the facility. They came in, and in 2 weeks, they pulled all their own power in, shot all their scenes, and had 1,000 people on site. And one day after that 2 weeks, you couldn't tell they were ever there. As far as project management went, it was pretty impressive to see how they operated. Drove the guards at Livermore nuts to have 1,000 people from Hollywood there. But as I said, there's 45,000 person years of experience in lasers and optics. It's also the origin of all of the Laser-Compton stuff that is the basis of the X-ray activities that I'm bringing down here to Irvine. I'm showing you a picture of the second and the third generation of 3 generations of machine. And the motivation for this activity actually occurs not in the X-ray regime, but what I would call the gamma ray regime, in the regime where the photon interacts with the protons in the nucleus more than it does with the electrons surrounding the nucleus. And I'll explain a little bit more about that in a moment. So we're going to talk about Compton scattering. Compton scattering is we take a laser and an electron beam. We take an electron beam that's moving, and we take a laser and we do a head-on collision with it. That laser causes a transverse motion in the electron beam. Transverse motion in the electron beam is a radiating dipole, and so it's a radio transmitter. But the electron is moving at near the speed of light, so what you see in the laboratory is a Doppler upshifted radio wave. That Doppler upshift can be 1,000,000x. So I can take a 2 eV green photon, and I can make it into a 2 MeV, 2 megavolt gamma ray with this process. Sounds great. There's a little problem, and the problem is that you're dealing with the Compton cross-section, and the Compton cross-section is about half a barn, about 6 by 10 to the minus 25 square centimeters, and that makes it very hard to have any efficiency out of this process. In fact, if you think about it, what you really want is to get every electron to be radiating. To get every electron radiating, I need something like 10 to the 24 photons per square centimeter to have a unity probability of radiation. If I have a 100 micron spot, that's about a 44 joule laser, right? So it's getting to be a little bit hefty on the laser side, but of course it's a cross-section thing, so if I make the spot smaller, if I make a 3 micron spot, I only need 40 millijoules, right? And that's kind of giving you a little foreshadowing of where we're going to go in what we do. Unity efficiency for 25 microamp of current would be something like 10 to the 14 photons per second, which would be really what you produce out of the largest synchrotrons on the planet. If you think about synchrotrons, synchrotrons are kilometer footprint particle accelerators that are in a circle. So the electron beam goes around in a circle at very high energy, and periodically it'll go through a set of magnets, which causes a transverse motion on the electrons, and that transverse motion causes radiation, and you get the same kind of radiation that we have, except that the period of that oscillation is set by the period of the magnets in the wiggler of the setup, and that period can be of the order of a centimeter or so, maybe a little less than a centimeter. Our period is set by the wavelength of light, which is a micron. So we have kind of a 10,000x difference in what we have on scale for making that oscillation, and that means we can take something that's kilometer scale and basically build it in the scale of the table that's sitting in front of you, right? That's one of the reasons why I got in this game. So to do this, the generic setup cartoon that we have is that we start with a common laser. We split that common laser into 2. One part gets converted into the UV and is used to hit a cathode and make an electron bunch. The other part gets amplified and compressed to a short pulse duration, Gerard and Donna Strickland's idea. And it does a head-on collision, and we, of course, get a yellow gamma ray coming out the other end, because everybody knows that gamma rays are yellow, right? Come out the other end. One thing I like to point out to people, well, if you do all of this right, a 250 MeV electron will give you 1,000,000x upshift and potentially very narrow bandwidth and very collimated. I like to tell people, and everybody in the audience will get this, you take a green laser pointer, the collimation that you have out of one of these systems with a 250 MeV electron is better than a green laser pointer. The spectral purity that you have is better than the spectral purity in your green laser pointer. It's not coherent. It's not a coherent X-ray or gamma ray source, but it's a very, very collimated source. One of the things I like to tell people, when you build these things, you don't use any photons. We have 10 to the 10 electrons in our electron bunch. We have 10 to the 19 photons in our laser pulse. So even if we had unity efficiency, we'd still have 10 to the 19 photons left. So it's not a very efficient use of the photons. And so one thing you can do is you can set up a cavity and trap the laser light in. And the way that we do that is we take infrared light, we go in through a dichroic mirror, we go into a frequency converter, we make green, and then we trap the green inside the cavity, and then we can have that green pulse interact with another electron bunch that comes down the train. And if you do that, you know, you can kind of get a 50x for free. So instead of having to build a 50x higher average power laser, we can just recirculate the laser light and get a 50x enhancement. I actually think you could easily take this to more than 100x, but this was just the first experiment that was done at Livermore. I won't go into other details of that. Now, if you're building an X-ray source, one of the primary metrics that people talk about is the brilliance of the X-ray beam. And they'll talk about peak brilliance, and they'll talk about average brilliance. Brilliance is the number of photons that come out of a unit area in a unit time, and a unit solid angle, and a unit bandwidth. Okay? So those are the synchrotron units that you have up on the other side. If you look at the light curve, which is the blue portion of a synchrotron, you'll see that most of the light is made out there between 10 kilovolts and 100 kilovolts. That's where synchrotrons are designed to work, because that is the wavelength that is roughly equivalent to the spacing of atoms and molecules and crystals, and synchrotrons are used to tell you where the atoms are in molecules and crystals. So that's, you know, not a shock. When you get above 100 kilovolts, synchrotrons don't make very much light. In fact, they die faster than exponentially. If you're to look at a Compton source, sorry, that's what you get when you press the wrong. If you look at a Compton source, you actually get better the higher the energy of the photon you make. And you get better because what's the problem in this Compton picture I had? The problem in the Compton picture is you have to get the laser and the electron beams in the same place in space and in time. The laser, we can focus to the diffraction limit. The electrons don't like each other. You know, they don't want to go to a small spot. If you make the energy of the electrons higher, you can overcome that electrostatic repulsion. The beam becomes stiffer, right? And with the right magnets, you can focus to a smaller spot. You can focus to roughly a linear smaller spot with a linear increase in electron beam energy. That means I've got a square smaller area. This is a cross-section thing, so I'm getting square more photons out of a square smaller area. It's a brilliance thing I'm looking at. I'm looking at photons per unit area coming out. So I'm going up in photon brilliance, like something like the 4th power of the electron beam energy as I go up in energy. And if you look out at a couple of megavolts, sorry, you're more than 15 orders of magnitude beyond the peak brilliance of a synchrotron. Now, I have a saying I like to tell people: when you go into a new field, you want to have a 3 order of magnitude advantage over the competition. Because by the time you get where you're going to go, the competition will catch up an order of magnitude. You'll find out you were wrong by an order of magnitude, and you'll still be an order of magnitude ahead of them. At 15 orders of magnitude, you got a lot of room to play. At 15 orders of magnitude, this particular region is where the photon interacts and makes the protons move around in the nucleus, as opposed to the valence electrons moving around. So it's the nuclear regime. Well, Livermore is a nuclear weapons science lab. There are plenty of nuclear physicists. So as soon as I saw this, I went around and started knocking on the door of all the nuclear scientists I knew and said, yo, we're going to have 15 orders of magnitude brilliance. What are we going to do? Got a blank stare, because nobody thought about what to do at 15 orders of magnitude. They never, why would they ever bother, right? There was no source. So this kind of led to a whole set of activities. It led to a white paper that I wrote back in 2004 that said we would do nuclear science with photons. Kind of the same, in my view, as the transition from 1959 to 1960 with the laser and the valence electron. You know, in 1959, atomic physics was whack it and look at it. You put the atom in a spark and you put a bunch of spectrometers around and you look to see what was going on, and you're trying to figure out from the passive signature that you had. The laser was invented in 60. Pretty soon you had tunable lasers, and then you could do tunable spectroscopy at the line width of the transitions you cared about, and you could have polarization, you could look at angular momentum, you could do all these wonderful things. Nuclear physics is still whack it and look at it when it comes to photons, and this is really a way that you change that paradigm in the nuclear physics world. There are a bunch of things you can do. Once you get above 1 megavolt, you can make pulse positrons out of this kind of source that has a lot of materials science applications. You can make isomer with these kind of beams. When you get above 5 megavolts, you get in the regime where the photon can fission the nucleus, and you have photofission. Of course, if you can photofission, you can also make fast neutrons with photons. And now you have a way of making pulse neutrons that are picosecond in duration that you can use to probe materials. So there's an entire cadre of nuclear science that you can do with this. We decided about a dozen years ago, I coined a term called nuclear photonics, to be the area of science where you would do this nuclear physics with the photon beams. And you know, a dozen years after I wrote that white paper, we had our first International Nuclear Photonics Conference. We held this in Monterey. We had about 140 people in 2016. In 2018, we held the meeting in Brasov, Romania, and we had 240 people. So that whole field has just gone nuts. You know, all the nuclear physicists are looking at this and going, that's the next thing we want to do. In fact, there's a $400 million facility in Romania. There's a reason why we held the meeting in Romania. That's being built just to do photonuclear physics or nuclear photonics. It's called the Extreme Light Infrastructure Nuclear Physics Facility. They have a gamma beam capability that's supposed to come online and have between 1 and 19 MeV out of it. Nuclear resonant fluorescence is the thing that we started looking at. Nuclear resonant fluorescence is the analogy of atomic fluorescence. Instead of making a resonant motion of the electrons around the atom, you're making a resonant motion of the protons inside the atom. Now, the difference there is that the forces that are governing where the resonances occur inside the nucleus are not just the electromagnetic force, it's the electromagnetic force plus the strong force. So those resonances are not dependent on the number of protons, they're dependent on the number of protons and the number of neutrons. They're not an element signature, they are an isotope signature. And the isotopic resonances for one isotope to another are just as vastly different as one element's valence electron signature would be from one to another. They're very sharp resonances. You can see the resonances in these pictures. This was a whack it and look at it study of nuclear resonant fluorescence. The nuclear resonant fluorescence transitions occur mostly in this range between 1 and 3 megavolts. Between 1 and 3 megavolts is a very interesting regime because it's the regime where the Compton cross-section is dying off and the pair production cross-section hasn't kicked on. And that is the position where every material in the periodic table is maximally transparent. So if you're trying to probe through something, this is where you want to go. A 2 megavolt photon, I could have a foot of steel and be able to see through it and something on the other side if I had a resonant on the other side. There are a number of applications. This was the primary application that led to, in total between Livermore and SLAC, $220 million worth of R&D. So after 9/11 occurred, there was a big worry about nuclear security, and in particular about nuclear security and the potential of a terrorist smuggling a uranium-235 weapon. So I'll give you Nuclear Weapons 101. There are two things you can make a fission bomb out of. You can make it out of plutonium-239 or uranium-235. You should never worry about a terrorist trying to smuggle in a plutonium-239 or a dirty bomb for that matter, because they radiate like hell, and all of the passive detectors we have mounted everywhere in the country will detect it instantly. You know, there's an anecdote of a woman who went to have her thyroid treatment, drove through the Holland Tunnel, and by the time she got to the other side, the police had a roadblock to pull her over because she had set off all the radiation detectors in the Holland Tunnel. Shouldn't worry about things that radiate a lot. I used to joke, a plutonium weapon will have a gravitational signature. The amount of shielding you would have to put around it to keep you from seeing it would make the truck sag, right? Uranium-235 takes lead the thickness of this computer screen. Every seagoing cargo container in the world, all 50 million of them that are shipped around the world every year, is thick enough to keep you from seeing uranium-235. So that is, in the security world, the grand challenge. Can you find that? And what I suggested at Livermore was, well, if we had the uranium-235 nuclear resonance signature, we could, right? By the way, the congressional report on this problem is that if a terrorist did smuggle one in, they would detonate it in Long Beach, or they would detonate it in Oakland. They wouldn't detonate it in LA, because if they detonated in Long Beach, every port in the world would shut down overnight, worrying that they have one. And it would be $1 trillion impact on the world economy overnight, right? So again, big problem, still not solved. You shouldn't sleep well, you know. Sorry to scare you. So, yeah. So the picture that we had, this is actually an X-ray radiograph of a truck, not done by a Compton source, done by a conventional Bremsstrahlung X-ray machine. And it is, if I look at that picture and I go, wow, this is incredible. It's really high resolution, everything, it's really nice. And you know, there's a couple of dark objects in it, including this dark thing that's hanging from the ceiling. Well, if that's not on the manifest, you're going to want to ask, you know, is that thing, yes or no, nuclear material? If you have a gamma laser Compton source at 1733 kilovolts and you illuminate that dark object, you will be able to, in a millisecond, say yes or no, it's uranium-235. So that was the motivation for the majority of the R&D that was done at Livermore. To solve this problem, what is it you ultimately need? You need something that's compact as a tunable gamma ray source, because you're sitting at a port, and real estate at a port is very expensive. It has to be robust. You're sitting in a port, trucks are driving by all the time. It's not a pristine laser lab with vibration isolated tables. And it has to be ultimately operable by somebody who's not a PhD physicist. You know, so somebody who is a dock worker, you know, doing yes or no, okay? And that R&D that we did wasn't just about writing science papers. It was about satisfying those three conditions. And when you satisfy those three conditions, you end up, when you scale back to the X-ray regime, and particularly to the medical X-ray regime, you end up with a very compact, very interesting source. Again, something the size of one of the tables you're sitting at. In the gamma ray regime, there are other applications. One application is the efficient mining of materials. When you do open pit mining like this, you take large chunks of rock out of the ground, you take them over to a crusher, you crush them and you make powder, you do a chemical extraction of that powder to make the metal that you care about, and then you have a tremendously large waste stream that you have to remediate. In fact, this is why most of the mines in the US have shut down. They're just not economically viable because they have to deal with all the chemical remediation. If, on the other hand, you had the ability to take the rock and pass it through the beam and have it trigger, you know, every time that you had something you cared about, and kick that rock out and let all the others go into a slag heap somewhere, you could increase the efficiency of that mining tremendously. We have people that are associated with the company that I'll tell you about later who were part of global mining activities, and when they add efficiency to do that kind of thing. These nuclear resonance fluorescent transitions are very narrow. They're about 10 to the minus 6 wide in the Doppler broadened transition at room temperature. Compton sources have been around since 1965, and they're generally 50% bandwidth. And so you really have to find a way to get to narrow bandwidth. If you can get to 10 to the minus 3, you have the statistical likelihood that there's no overlapping isotope with the same resonant energy. So our goal was always to try and get to 10 to the minus 3 bandwidth. When you make a Compton source, I said it was monoenergetic, but it's really only monoenergetic in the forward direction. You get 4 gamma squared times the input photon energy, gamma being the normalized energy of the electron beam, as the upshifted energy. You make all energies of photons, but they're angle correlated. So if I take the initial beam and I put an aperture around that beam, I will make the spectrum narrower and narrower until I get to the point where closing down the aperture doesn't make it any narrower, it just makes the output less, okay? Minimize that, that bandwidth at the narrow aperture setup. So also, when you talk about this narrow bandwidth setup, the collimation of the beam becomes extraordinary. That collimation is dependent upon the quality of the electron beam. In the electron beam world, there's something like m squared, for electron beams. And if you make a very good electron beam, then you can have a very, very collimated. That collimation could be, instead of being milliradians like a laser pointer, it can be 10 to 20 microradians for the collimation. So it's a very different beam than you might think of. There are a number of factors that play a role in what the minimum bandwidth is. Obviously, if the laser bandwidth is more than 0.1% or the electron energy spread is more than 0.1%, you're never going to get below 0.1%, right? So initially, people in the Laser-Compton world tried to use petawatt lasers or very short duration, 10 femtosecond, 30 femtosecond lasers, because they were trying to make short duration X-rays. In reality, all they did was imprint the bandwidth of their 30 femtosecond laser pulse onto their X-ray source. What you really want is a few picoseconds, because that puts you in the right place. If you have a focal spot of a few microns, that's kind of the right space. You don't have a delta K effect that's broadening your bandwidth. You don't have a radiation pressure. If you do everything correctly, really it's the electron beam. It's a good message to give to the optics community. It's not our fault. It's the electron beam guys' fault. If you work really hard, you can get an electron beam. It should get you to 10 to the -3 bandwidth out of the source. Again, typical Compton things that people have done in the past, 30%. All right, so it really is an effort. That was what we spent a lot of our R&D doing at Livermore. This was our second generation machine at Livermore. It's called the Thomson Radiated Extreme X-ray Source. Thomson radiation is the elastic version of Compton scattering. It really doesn't hold for what we have, but C-Rex isn't as good a name as T-Rex, so we use T-Rex as the name. It was an S-band system. S-band is 3 gigahertz radio frequency. It's made out of the same S-band Linac sections that are used at the Stanford Linear Accelerator, right? It was the world's brightest source at 500 kilovolts. This is a beam. The polarization is horizontal, so that's the dipole pattern that you're seeing coming through the aperture. We made it tunable by changing the energy of the electron beam. And most importantly, we matched exactly what our model said. And one of the beautiful things about Compton scattering is that it is a cross-section thing. And if you stay in the linear regime, you can absolutely calculate to the nth degree exactly what the X-ray source is that comes out. If you know what the electron distribution is and you know what the laser distribution is, you get what the X-ray distribution is. With that source, we did a very interesting experiment. We detected the presence of lithium shielded behind lead. Now think about that for a second. If I have an X-ray beam that can make it through the 82 electrons per atom of lead, the 3 electrons per atom of lithium aren't going to do anything to it, right? X-ray absorption or X-ray radiography is an electron density radiography. So the 3 electrons around lithium, you're not going to be able to ever see them behind lead. But what we did is we tuned the Compton source to 478 kilovolts, which is the lithium-7 nuclear resonance. So that's when the proton resonance kicks in. And we use that proton resonance to tell us where things were. Great, except it took 6 hours. It took 6 hours because the brilliance that we had on line center was pretty low. I mean, what matters is the number of photons that are in that 10 to the -6 bandwidth versus the number of photons that aren't. The signal divided by the noise, right? It's pretty simple. So you want to put more and more photons on resonance to make a narrower and narrower bandwidth source. There were a number of applications in the security world that people wanted to do. They wanted to do treaty verification. If you pull the missile up, does the center of the missile have the thing in it that you care about, right? And if it is, then, good. And if it doesn't, then you ask, where did the plutonium go or where did the uranium go? To do that mission, you need a spectral density that was maybe 4 or 5 orders of magnitude beyond where we were in the T-Rex experiment. And you needed something that would be portable. You could drive around. The T-Rex experiment was nice, but S-band accelerator technology is not portable. To do the uranium-235 would take an accelerator longer than the width of this room. You weren't going to ever take it anywhere. And I tried really hard to figure out how to make it smaller. The conclusion we came to was we went across the bay to our friends at the SLAC National Accelerator Lab, and they had been developing under a separate contract, compact RF accelerator technology in X-band. X-band is 4 times the frequency of S-band. It's 12 gigahertz. And at that higher frequency, you can achieve a higher gradient in the accelerator structure. In fact, they can go from 10 megavolts per meter to something like 150 megavolts per meter. And since we only need 250, our accelerator goes from being, 15 meters long to being a meter long, meter and a half long in our setup. So that was a real game changer for us. So we leveraged a great deal of activity that was done. All of that work at SLAC was done in anticipation of the machine that will be built after LHC shuts down, after the machine that found the Higgs boson shuts down. That machine is supposed to be multiple TeV in energy for the electron beam. It's supposed to be 30 kilometers long. The real estate is the big cost driver, so the higher the gradient you can make for the accelerator, the smaller the footprint, the lower the cost. And the cost currently is something like $60 billion, and that's a physicist estimate. So, that's not going to work. So we built an X-band accelerator at Livermore. This is the test setup. The accelerator is actually the bit right here at the top. Everything else is what I would call R&D stuff that you use to diagnose the accelerator setup. Of course, we had to give it a name. We named it Velociraptor. We named it Velociraptor because that's a smaller, faster, smarter dinosaur than T-Rex. It's actually an acronym. It stands for Very Energetic Light for the Observation and Characterization of Isotopic Resonances in the Assay and Precision Tomography of Object Radiation. I'm not doing another dinosaur, right? That's right, it's a backronym. That's when, they say put your tray table up and your seat back in the upright position. That's when you pull out your notepad and start doing acronym development. That machine had a modern solid-state modulator and klystron, which gave a very stable RF pulse. We designed our own photogun for that setup. Excuse me. Going backwards in the wrong direction here. There. We designed our own photogun for that, which the photogun is where all of the distortion in the electron beam emanates. You want to have a perfect electron beam coming out of the photogun so that you have any hope of reducing the energy angle spread of the beam coming down the pipe. We did a development of that. We built the gun. We tested the gun. We wrote papers on the gun. We started with a design that was from SLAC, and they thought we were idiots, and then they came over and looked at it, and then they adopted and built one themselves, right? So it was kind of gratifying to see that they thought that we actually could do something with accelerators. Oh, I should point out, the guy in the purple shirt, raise your hand. That's Yun Wu. Yeah. Yun Wu did his graduate work here at UCI. He spent more than a year at Livermore working on the Compton stuff. He's now with the company that's associated with the Compton stuff that's over in the research park. I'll get to that story in a second. Okay. With that setup, you can think of different ways of doing Compton scattering. In fact, one of the ways that you can do Compton scattering is let's put an electron bunch in every RF bucket of the accelerator. We run our accelerator at 11.424 gigahertz. Don't ask me why it's some US thing versus European thing. They run at 12 gigahertz. We run at 11.424. 11.424 is 87.5 picosecond spacing, so we have an electron bunch every 87.5 picoseconds. You can ask me afterwards how we make an 87.5 picosecond train of laser pulses to hit the photocathode. That's a very interesting story, and we have a grad student, Michael Segerovich, back here, who's going to be working on that. Right? And then you can take that train of electron bunches, and if you have a large laser spot, you can have many electron bunches in one confocal parameter of the laser focus. And every one of them sees the same laser field because you don't use any laser photons when you do Compton scattering. And so now you have a way of getting more efficiency out of your system, and you end up with a more collimated beam because the beam area is bigger. So we wanted to test whether we could put multiple electron bunches down the accelerator and not have one distort the next. What happens with an electron bunch when it goes down a conducting structure is it can create a wake, electromagnetic wake. That wake can perturb the next electron bunch, and if that does enough perturbation, then the next electron bunch doesn't have the right energy, and then you don't have the ability to stay on line center. So we wanted to test that out, and we started with a long duration laser pulse, which was a commercial neodymium YAG, frequency double neodymium YAG laser that was just lying around, and we made 400 picocoulomb electron bunches, and we made those with a Hyper-Michelson interferometer. So laser pulse comes in, it gets split again, it gets split again. And then you recombine, and you can set the spacing by where you put the optics and delay lines, right? What setting you have. To align these two things together is a trick. You have picosecond entities that have to arrive at the same time in the same place and space. And they have to arrive in 10 microns, within a micron or so of each other. And so the way that we do that is we put inside of the accelerator, we drop down a small cube, precisely machined cube of nickel. And on one side, the electrons hit the surface of the nickel, and they make transition radiation, visible light. And on the other side, the laser hits the surface and bounces off and is reflected. And you can image both of those on a camera. And then you can pull the knife edge of that corner out and see if those two things come together in the same place. So we can get them aligned at the same place. We don't have the timing right yet. And then we can put a street camera on and look at the laser pulses. Actually, the timing in this case is pretty easy because we had a nanosecond long thing hitting a train of 87.5 picosecond spaced pulses. So that was pretty easy, but you can use the street camera to get the timing right. The light that comes out goes through a back-thinned optic. This was an X-ray experiment, not a gamma ray experiment. That back-thinned optic was thinned so that you could get the X-rays through the setup. And what you see is what the theoretical beam profile should look like coming through that 45-degree optic, with the back thin being the aperture that you're looking at. That was the theory. That was the experiment. That's the theory. That's the experiment, right? That's some of the best stuff I've seen, right? There was some stuff that I had graduate students doing back at Stanford that had to do with ultra short pulses where autocorrelations matched as good as theory, but this is pretty close. That's again Yun Wu, and he gets another round of applause. You take the line outs. There's a whole bunch of things you can do with the line outs that show you what's going on in the beam. I'm not going to go through those, but one of the things you can do, you want to know, is this a monoenergetic beam on axis or not? Well, if it's an X-ray beam, what you can do is you can take a foil of material whose K edge is slightly above or slightly below the maximum energy you can make in the beam. K edge transmission is shown on the right. The energy as a function of angle is shown on the left. If I superimpose those, you can see that the on-axis stuff is going to have a big attenuation versus the off-axis stuff. And what you should see is something like that when you put the foil in the beam. And that was what we saw when you put the foil in the beam. And so I had a bunch of guys from GE Central Research come by and see the stuff because they wanted to know, was this stuff with monoenergetic X-rays in the lab really real? And it was one of the best days ever. They're sitting in the control room, and we turn on the system and we put the foil in front of the beam, and the hole shows up. The two GE guys jump out of their chairs and go, "We've seen monoenergetic X-rays." It was fun. You can do that over and over and over again. These are 300-shot exposures. This thing is stable. You always hit the beam. It always makes the same energy. All of that's great. We extended to 16 bunches, and you can see that the energy our ability to measure the energy of the electron bunches, they were all the same. And if you have 1,000 bunches, you could think about having a different setup where you make a bunch train and a pulse train, and you focus the pulse train and the bunch train to a very small spot, and then you could get close to unity efficiency out of the setup. That's actually what we're trying to do here, is this particular arrangement. Again, we have to have an 11.424 gigahertz train of laser pulses. I'm not going to explain how we do that, but you can ask afterwards because it's cool. Okay, so that led us, after $220 million of R&D at Livermore and at SLAC, to the question of tech transfer. Okay, the Industrial Partnerships Office is right there at Livermore. After 3 years of negotiation, Lumitron Technologies secured the license to the 13 patents that are in the portfolio that are related to Laser-Compton activity. I'm the sole inventor on 10 and the co-inventor on 3 of those patents. They cover laser aspects of how to make various laser components. They cover architecture with respect to how you do optimized Compton generation, and they cover a set of applications. In fact, the last ones have to do with medical applications and methods by which you might be able to make the theoretical minimum possible dose X-ray imaging We have that building is 5201 over in California Avenue in the Research Park. Inside of that building, Broadcom very nicely left us this high power microwave lab, which is a beautiful facility for setting up lasers and accelerators. So we opened our doors on July of this year. Yunwoo joined us less than a month ago. I think some of you may know Ferenc Roxy, who I think worked at LensX and Alcon and that company. He was actually the first hire into this activity. We're in the midst of trying to construct what we call the HyperView KV machine. This is an artist rendition. It's not the actual thing that would be built. The patient would lie on the table would move back and forth in front of the beam that comes out of the Lumitron machine. It would be collected on the detector and you would build up your image in that fashion. If you do this, compared to a medical X-ray machine, medical X-ray machines are built the same way that Wilhelm Röntgen suggested or discovered in 1896. They take an electron beam, they slam it into a metal. When the electron beam comes to rest, it radiates X-rays, and it radiates X-rays into all angles and all colors. It's kind of like a flashlight, right? The resolution you can have in an X-ray image is set by how small a spot you can make slamming into the metal. Typically in a medical X-ray tube, that's 600 to 800 microns. In our case, it could be the diameter of the laser spot. It could be a micron, maybe half a micron if you're using frequency double light. So you could go 1000x. When you take a medical X-ray, if you do a chest X-ray, they'll set the X-ray tube voltage to around 75 kilovolts. That will make a majority of the X-rays at 60 kilovolts. 60 kilovolts will penetrate and make the shadow on the screen, but you also make copious amounts of 50, 40, 30, 20, 10 kilovolt light that illuminate your body, don't go through you. They only cause ionization and they cause damage. That's dose. If you have a machine that only produces one color, you already knock down the dose by 100x. And there are all sorts of ways that you can play games with the timing and with time-gated detectors to reduce the dose even more. So there's wonderful things you can do there. And of course, if you've got a tunable source, you can tune to the K-edge of anything in the periodic table and use it to identify the material that's there, or you could tune to the isotope resonance if you're at higher energy. What does 1000x look like? 1000x is sometimes hard for people to wrap their heads around. So this is a normal chest X-ray. 1000x, if this is a 1080p screen, is 1 pixel, right? That's still a little hard to imagine. So we stole a picture or an ad campaign from Bentley to demonstrate what 1000x. Let's assume that this image is 1x. That's your chest X-ray, and we're going to zoom in 1000x, right? So that's 1x resolution. This is what you get at 10x resolution. That's 10x. Now you can see there's a Bentley on the bridge. Shock, it's a Bentley ad campaign. This is what you get at 100x. You can see there's a driver, it's male, he's got glasses on. You might even be able to make out that there's a logo on the seat, but maybe not with this screen and the lights on the passenger seat. And this is what 1000x looks like. Okay, so now you can see the stitching of the logo on the seat, and we've got a monoenergetic source, so in principle, you could even tell what the stitching's made out of. Right? So again, remember, standing on the Golden Gate Bridge, somebody's walking on the bridge, you're going to see the stitching in their clothing and tell them what the clothing is. You start talking to doctors about that kind of thing, and they just, it's quasi-limitless. I'm going to give you 2 examples to end the talk. Right? First one is clinical trials. When you do a clinical trial, a drug test, you start with a little guy like this, very cute little guy. You create identical versions of him by cloning. You give the disease identically to those mice. And then you give the treatment identically to those mice. And then you kill them off one at a time, and you dissect them, and you take a look at what you found to try and follow the progression of the treatment and see if it was effective or not. You don't image the individual mouse because that mouse is 100 times smaller than you are, and you don't have the resolution to see what's going on there. If you've got a monoenergetic synchrotron-like light source, you can do much better. So the next picture I'm going to show you, I showed to the Chow Family Comprehensive Cancer Center's annual meeting, and the doctors in the audience gasped when I showed this picture. This is an actual picture taken at a synchrotron with a photon density on the detector that is less than what we should be able to make with a machine that fits on this table. This is a 3D tomograph of the mouse, right? And you can zoom in on the bones. I'm sorry, it's going to delay because we're doing a Zoom presentation, so that it's not going to rotate smoothly. You can zoom in on 10 micron features in the ear bones of this mouse. This is another beautiful one. This is a mouse embryo, okay? So same group at a synchrotron in Japan, took a mouse embryo. Mouse embryo is maybe 3-4 millimeters in size, and they do the tomograph, and then you can slice it up any way you want. And you can see every organ inside, every bone inside. You know, again, the cancer guys can't believe that you can do that. This is just, you know, it's a game changer for them. This is also a game changer, I believe, for the 3D manufacturing world. Because when you're manufacturing 3D metal parts, you're printing at kind of 10 micron spatial resolution. You don't have an X-ray source that can actually image those parts, and certification is the big deal. Livermore, when I left, was spending between $50 and $100 million a year on R&D on 3D manufacturing of metal parts because they want to make weapons components out of, with 3D manufacturing. And certification was the issue. This is a way that you could actually image at the resolution that you're printing at. And if you were making a multi-component part with multiple metal parts, you could image each individual constituent one at a time. So one of the other reasons why I was very happy to come here was that UCI has one of the best 3D manufacturing activities in the engineering department. If you talk to Big Pharma about this application, it costs $1 million a day to bring a drug to market. It's pretty easy to imagine that you could take a few $1 million out of the picture if you could give the disease identically to 10 mice and give 10 different treatments and follow each mouse individually to see what was going on. Last application I want to show you is a thing that I have a great story about UCI on. There are a large class of compounds and drugs that will bind to the surface structure. This is meant to be a blood vessel with cancerous material growing on the outside, and the purple stuff is meant to be a drug that binds to the surface structure of the cancerous material. There are a lot of these compounds that are out there that will bind to the surface structure because the surface structure is keyed in a certain way and you can make things. And the strategy that people have is to try and deliver dose locally. That is, they'll add a radioactive element to this drug and give it to the patient in hopes that they will give radiation directly where the cancer is. There's a cadre of people at Livermore who were trying to do this. The oncologist will tell you, hold on a second, it's not as good as you think because the compound accumulates in other places in the body like the pituitary gland or the lymph nodes. So you might cure cancer of the prostate and give cancer somewhere else. And then the other problem is, let's say you manage to only give the drug, have it delivered to where the prostate was. Once you've killed the disease, unless the body has flushed it out, you might still be giving radiation. So you might go from a disease state to a healthy state back to a disease state in the setup. We can take a different strategy, and that strategy is we could start with a benign heavy element, things like gadolinium, gold, platinum, tag those onto the compound. The chemistry, organic chemistry of gold is well known, so doing that's pretty straightforward. And then what you do is you do differential absorption imaging, a picture right below the K edge and right above the K edge, 1% change in the energy of the Compton source. Everything in the body has the same cross-section, and that 1% change, except for the gold, has an order of magnitude change. Subtract those two pictures, and you get just a picture of the gold, and the gold is just where the disease is. But it's better than that, because when you do a K-edge ionization of gold, you knock out the 1s electron. That leaves the gold in a very excited state, and what happens is a 2p electron falls into the 1s vacancy, and a 2p electron flies off to conserve energy and momentum. A 3D falls in to fill the 2p hole, and a 3D flies off to conserve energy and momentum, and you get this Auger cascade of electron ionization. All of those extra electrons don't go anywhere except local to where the gold is, which is where the cancer is. So now you have a way of seeing the cancer and treating the cancer without ever moving the patient. So conventional X-ray imaging, you have K-edge imaging, breast imaging here in this case. you have the ability to go and treat the disease. The ability to diagnose and treat at the same time is called theranostics. Unfortunately, there was a company called Theranos, which has ruined the word theranostics for everybody. But that is the generic term for this kind, and it is a holy grail in the medical community. There is no good treatment that way right now. I'll end with an anecdote. In April of 2016, I was in Sydney, Australia. The co-founder of the company is Australian. He has founded 22 separate companies. None have failed, all in the medical or environmental world. He has a huge cadre of medical physicians who are well known that are on retainer with him to ask questions. I convinced him to get us a conference room in a hotel, lock the doors, and put 10 people around the room and go around and ask what we could do, what the benefit would be, what the value would be, et cetera, and go around in a circle. And when I got to this story, Phil Stricker, who is the leading urologist in Australia. If I get prostate cancer and I'm in Australia, I'm going to Phil. He's the guy, right? And his comment to me was, wait a minute, does this mean I can see the disease and treat the disease without having to move the patient? And I said, yes. And his comment was, well, that changes everything. Because in his world, they can find the disease, but then they have to put an X on you, and then they have to haul you into the operating room, and then they have two choices. They can either take too much, which isn't good, or they can take too little, which isn't good, right? And they're not happy about either one of those. So see it and I can treat it and I never have to move you. That's fantastic. In fact, his comment was, if this really is true, you'll never remove a breast, you'll never remove a prostate again. Kind of motivational for doing this, right? I come down here in November of 16, they're recruiting me to come and bring this activity. I was going to retire in January and do this in Pleasanton, the city beside Livermore. And so they bring me down in November, to do this. And I met with Charles Lamole over in the radiation oncology department. And he has, Chris, does that mean that you could see the disease and treat it without moving the patient? I said, yes. And his comment was, you guessed it, well, that changes everything. And I realized at that point that having the company here and having my academic activity here, where you've got the end user communities that really understand what's going on, was really the best thing to do. So, after, there we go. Okay. So you are here, astronomy is there, Beckman, Sprague Hall is the med school, applied innovation. Lumitron is across the street from where applied innovation is right now. It's the corner of Bison in California, and it's about 3 buildings away from where the COSI lab's going to be. So after 3 complete generations of machine development at Livermore, $220 million worth of R&D at Livermore and at SLAC, we now have the facilities, we've got the funding, we've got staff at the company, we've got students at the university, and we've got the environment now to really go and try and change everything. Thank you. I'll put out my recruitment note. We are looking for high power laser people. The interaction laser that we're going to make is going to be between 100 watts and a kilowatt. It'll be diode pumped. We have several designs on the books right now. We're looking for people that are interested in that area. We have needs for project engineers. We have needs for mechanical engineers and for electrical engineers. Anyway, I'll take questions.
Thank you. Let's do questions. When can I start?
Yeah.
When can I start?
When can you? Oh, when can you start? Okay. Monday is probably good. No, it's only Wednesday. You can start tomorrow. We've got 11 people now in the company. We're ramping up to probably around 25 in our current plan. The plan is to build 2 machines initially, 1 machine that stays in the company on which we develop applications and other IP. This is kind of a fun field to be in because everything you put in front of the beam is new, right? So the potential for generating new IP is tremendous. From an optics perspective, I didn't mention this, but there's an entire technical field of X-ray optics that has been explored in the synchrotron community that is of relevance to what we do, but isn't exactly what we do. So it's a wonderful position to be in because you can build new things with pretty low risk of them actually working. You just have to design them correct. So in the X-ray regime, the index of refraction is less than unity, and it's very close to unity. So a positive lens looks like a negative lens in the visible. And the focusing power is very weak. So if I had one lens, it might take me 50 meters to focus the beam. But I can lithographically make these lenses because the beam isn't very big, and I can stack lenses up one dimension at a time, make two of these things, and I can make a focus that's maybe this far. Well, those foci can be 100x demagnification. So I could take my, 10 micron source size, make it into 100 nanometer source size. There's all sorts of wonderful do all sorts of stuff that people haven't really explored. Yes?
How would the gamma be generated?
So that's actually a very good question.
Focus on prostate.
So we wouldn't actually use gamma beams for that. We would use a source that is tuned right around 78 kilovolts, which is the K edge of gold. And at 78 kilovolts, you can use a lot of these synchrotron tricks to make X-ray optics. You can make a fan beam if you want. You could make a focusing beam if you wanted. You could make a two-dimensional expander if you want. There are a number of things that you could do in that realm. And in the prostate case, naturally collimated coming out of these things, the on line center beam is hundreds of microradians. So it's already very, very collimated. When people do radiation therapy now, they use megavolt light that's made from a Bremsstrahlung source that is spewing out in all directions, and they have lead collimators that try and collimate the beam. Well, those collimators are really crude in the sense that they are millimeters of kind of accuracy that you have. So you're a couple of orders of magnitude better than what they're going to do just out of that, that approach.
Okay, but how would you manipulate the gamma?
So the gamma beams, you can play the same tricks with these cascaded optics. Of course, you have to have more optics to do it because the focusing power becomes less and less for each optic. It actually turns out that the transmission doesn't change a lot because while the index is getting closer to unity and the power is getting less, the absorption is getting less at the same time. And so you have more optics, but you still have 10 to 20% throughput of the optical arrangement. And I'm happy to give up 10x of my photons if I can focus the beam to, sub-micron spatial size. The optics that have been used, a couple of different things that people have done. They've done silicon, they've done gallium arsenide as semiconductors. And again, these are one-dimensional focusing, right? So they'll make a set of one-dimensional lenses, right? And then they'll make an identical set and rotate the thing 90 degrees. So they'll make one set of focus. It's like having two cylindrical lenses to make a focus, right? There's that approach. There's also a coining approach where people will take copper or gold and they will press the parabolic surfaces into the coin and then stack the coins together to make the X-ray optics. Both of them work. Little more artwork involved in the coining approach than in the lithographic approach, but it is two-dimensional naturally when you do the coining approach. Yeah.
I'm really interested in photolithographic processes for semiconductor manufacturing. The big challenge is UV, and traditional product undulators, fridges, and things like that. Has anybody in this Laser-Compton regime looked at EUV and photolithography as opposed to?
So the photolithography application requires a real flamethrower. It requires watts of light. This is not going to do that, right? It's a precision tool. What this might play a role in that community is in doing metrology of masks and metrology of Fresnel lenses and optics that are in the setup. But it won't be the illuminator. Not unless you're going to just write one spot at a time and you've got some special thing. But doing large-scale lithography, this is not the approach. You're not going to beat tin oxide discharges with this.
Any more questions? So, we have something for you?
Yeah.
Something for you. In this tradition, we provide our speakers with a 1-year membership
Oh,
to the Optical
thank you.
Society of Southern California.
Thanks very much.
Okay.
Thank you.
Thank
Thanks.
Thank you so much for
Yeah,
coming. Really
you're welcome.
appreciate it. And you got a great audience.
Thanks.
Everybody.
And, you know, if you have any other questions, I'm cbarty@uci.edu. You can look me up on the web for the university. I'm happy to take questions anytime.
And take some food home, take some water, soda, stick around. Nobody's picking us out right away, so food home, got water, got some fun.
Yeah.